Exception to octet rule. It is not always necessary for all compounds to obey the octet or duplet rule. Some of the compounds are stable without obeying octet rule. 3 exceptions to octet rule: incomplete octet, expanded octet, and odd electron. For incomplete octet, the central atom has less than 8 electrons in its valence shell. Expanded octet, the central atom have more than 8 electrons in its valence shell, and for odd electrons, the central atom contains an unpaired electron. For exception to octet rule, focus on the central atom to categorize which class for exception to octet rule. Incomplete octet occurs when the central atom has less than 8 electrons in its valence shell. Element group 2 and 13 in period 2 with low metallic properties do not donate but share the electrons. For example, BeH2. So this BeH2 has total valence electron of 4. So these 4 valence electron used for bonding electron. Both H achieve duplet electron arrangement, but for Be, it only has 4 valence electron. It doesn't obey octet rule, and it's less than 8 electron of valence shell for Be. So this is incomplete octet. We focus on the central atom. Other than Be, for BF3, it's also incomplete octet. You can make multiple bonds for BF3, making this B atom obey the octet rule, but the formal charge are not all 0. These formal charge are all 0, which means this BF3 structure is more stable than the BF3 structure with multiple bonds. So that's why we choose this BF3 structure without the multiple bond. So for BF3, it's in incomplete octet. The example for incomplete octet for central atom, Be, B, and Al. If this 3 becomes the central atom of a compound, it won't achieve octet configuration even after sharing electron with other atoms, and don't make multiple bond for Be, B, and Al because they are stable even though they are incomplete. Expanded octet occurs when the central atom has more than 8 electrons in its valence shell. So we focus on the central atom. It has, for this one, it has 2, 4, 6, 8, 10, 12 valence electron. And for PCl5, P atom has 10 valence electron. It usually involves non-metal atoms of period 3 and beyond which have empty 3D subshell. So this sulfur atom and phosphorus atom has empty 3D subshell, so they are involved in expanded octet. They don't obey the octet rule. Odd electron molecules contain an unpaired electron. Focus on the central atom. It contains an unpaired electron. Most odd electron molecules have a central atom from odd numbered group, such as nitrogen, odd number group, group 15, chlorine, odd number group, group 17. Not even odd number group. So this nitrogen, group 15, has 1 odd electron. Means this electron has no pair. This electron has pair, this electron has pair, this electron has pair, but this electron has no pair electron, so we call it odd electron. When you have odd electron at the central atom, it is odd electron molecule. So odd electron molecules also an exception to octet rule. It is stable like this. It is stable with odd electrons in the molecule. Resonance structure, 2 or more Lewis structure for a single molecule that cannot be represented accurately by only one Lewis structure. So structures have the same relative placement of atoms but different locations of bonding and lone electron pairs. For example, we have ozone molecule. These two are resonance structure. It's a stable O3 compound. So this oxygen obey octet rule, this oxygen obeys octet rule, and this oxygen obeys octet rule. And if you calculate their formal charge, both molecules have the same formal charge. But we show resonance structure because this multiple bond is not necessarily to be on the left side, and the multiple bond for this one is not necessarily to be on the right side. It can be at the left and at the right. That's why we use double-headed arrow to show both of this structure are correct, because this multiple bond can be on the left, but the multiple bond can also be on the right. So you cannot just show one structure to show the ozone molecule. You have to show both because the multiple bond position is not fixed on the left and it is not fixed on the right. It can be at any. That's why we use this double-headed arrow to show their resonance structure. Same goes to CO3 2-. This double bond can be on the left and on the below part and on the right. All of their formal charge are the same, so that's why you have to use double-headed arrow to show their resonance structure, because this double bond is not necessarily to be on the left, not necessarily to be on the bottom part, and not necessarily to be on the right part. It can be at any position. That's why you have to use the resonance structure arrow, double-headed arrow.